storage. So mass storage systems of operating systems look at what it is by concept, the structure of the disk attachment, disk scheduling, disk management, swap space management, RAID, and redundant disks, so RAIDs of a disk, disk attachment, stable storage implementation, storage management devices themselves, operating systems issues, and then performance issues that are associated with them. So that's basically the objective of today's lecture and chapter 12 of the textbook. So in terms of what we're looking at, we're describing the physical storage of secondary and other storage devices that results in effects on the uses of the particular devices. I'm going to talk about hard drives and talk about how they have spinning, how they work in terms of the mechanical components of it, but this is not a computer architecture course, so I'm not going to get into the nitty-gritty details of building hard drives. I could take an entire course on that. Instead, I'm going to cover basically the concept in terms of how operating systems are designed to make use of it and not to wear out the hardware. But keeping in mind, some of this data is already a little bit outdated because hard drives are now, in fact, you can buy computers now with what's called flash media or solid state drives. They don't have moving parts and components, which offers some more advanced techniques for operating systems in terms of implementation of the access to these storage medias. So I'll talk about that a little bit as well. And discuss the operating system services that provide the mass storage, including RAID and some of the other ones, perhaps a little bit. So what do I mean by mass storage structure? These are referred to in the old days as magnetic disks, provided which bulk secondary storage for modern computers. Keep in mind, mass storage is the largest, which is why I guess the mass word comes to it. Also referred to as secondary because it's not primary. Primary is anything on the board, anything close to the CPU, your RAM, your DRAM, your cache memory, registers. That would be primary memory, primary access. Secondary, the second half of it, is the long term. It's the non-volatile. It doesn't go away when you turn the computer off. So a thumb drive is mass storage, a hard drive is mass storage, a tape drive, a DVD, CD-ROM. These are all mass storage devices. In terms of the characteristics, they're the slowest accessible type of memory. They're the farthest away from the CPU, so they take the longest to go get, and they end up with issues in terms of speed, accuracy. Not to say that they're slow by far. The mechanical device itself that's facilitating the mass storage has a speed component related to it. It might be in terms of disk access time. How long does the mechanical arm take to go from one end of the disk to the other? And I'll talk about that in a few minutes. And a lot of the issues associated with just the mechanics of the storage media, which is why kind of the solid state approach is a little bit more effective because we don't have as much, it's flash memory. It doesn't have as many problems as other types of memory does. So in terms of magnetic disks, drives that rotate at 60 to 200 times per second. Some disks, in fact, you see this if you ever pop open the lid on your computer and you take a look at the outside of your hard drive. It'll say what speed it has, access speed, rotation speed. And you'll see some specs on there. Faster the drive, the faster it is to use on the computer. Will make a significant improvement if you go out and buy the latest and greatest fastest drive. Maybe you'll notice a little bit, but you're still working with the operating system and the operating system's ability to actually read the information. So it's not just the speed of the drive that makes an effect. We have transfer rate. That's the rate at which the data flows between the drive and the computer, which is a factor of a bunch of different calculations that go into that. It's not identical to what's written on the outside of that hard drive. So the transfer rate, is the rate after we go to the disk, we find the information on the disk that we bring it back, and it's an operating system calculation. We can have position time or random access time, which is the time to move the disk arm to the desired cylinder, or the seek time. Sometimes you'll see seek time in terms of a spec that's on a hard drive. And time the time for desired sectors to rotate underneath the head. So we have rotational latency, or latency in general, that we have to consider. Head crash as a concept that results when the head makes contact with the disk surface. That's not really a good thing. In fact, that corrupts data. In fact, that's one of the things that makes a hard drive unreliable. You shake it up, the head's going to smash against the drive itself, the plates themselves. When it hits the disk surface, it's going to damage it. It's a sharp needle that's going to essentially, it's kind of like a record. If you go think about the old records, if you're familiar with vinyl records, you know, one of the big things, problem with them is scratches. So the record got scratched, the record got damaged, something happened to it. Every time you read it, that little damaged spot, maybe got heat exposed, or you know, some key hit it or something. Not going to read correctly. So the same thing happens with your hard drive, actually. So the way the operating system gets around it is it just doesn't store something in that little bad sector, and it stores it in other sectors. Disks can be removable, or they can be fixed in the system. Drives might be attached via an I/O port or an I/O bus. So we refer to different types of buses. Buses vary. They include EI, Extended IDE, a.k.a., which is probably the more popular, SATA, even more popular today, USB, kind of slow but popular, SCSI, faster, better, more popular than USB in terms of a hard drive. We have a host controller in the computer. It uses a bus to talk to the disk controller, built into the drive for any type of storage array that might exist. And here's what we're talking about here. We have this is soon to become an antique model. It isn't, though. We still have computers today that are using it. Even notebook computers use the same type of drive mechanism. We have a moving head disk mechanism, where we have plates or platters that are stacked on top of each other, and we have an arm, and an arm that they're on a spindle. And the arm goes around, and it comes through and finds, depending upon which sector, which cylinder, where the particular piece of data is on this disk, the arm finds it, and then it reads from that position. So we have track 1, track 2, track 3, we have platters in here. It's sort of a cylinder that rotates. If you've ever seen a hard drive work, it doesn't really look, you can't really see the detail, the reading underneath and on top of the platter, but we can have multiple arms, we can have a single arm. We can have each one of the platters can have its own, each one of the platters in this picture here actually has its own arm. The arm is the mechanism that's coming out. This is mechanical. This is what I was saying before. I was calling it a mechanical drive. You know, anything that's mechanical wears out. It's kind of like how many times will the arm, it's like that IKEA commercial, how many times will the arm go across and read? Eventually the arm gets, you know, a little squeaky, and the drives make a little noise. Sometimes the arms themselves aren't secured properly. They get a little loose, and then they stop reading. Or they get loose in usage, perhaps. So anything mechanical is, the more you use it, the more it's going to break down on you. And that's one of the problems with hard drives. And for everyone who thinks that their hard drive is going to last forever, don't think that way. Don't stick all of your nice little photos from your digital camera onto your hard drive and think that 10 years from now when you turn that computer on that the hard drive's going to spin, that the mechanics are going to work. No, they're probably going to get corroded by then. So hard drive has a shelf life. And I believe it's 4 years, but I can't remember the spec on it. And everyone's thinking, oh my God, how long have I had my computer? After about 4 years, depending upon the manufacturer of the drive, you should probably upgrade. Probably should start burning your stuff off that drive if you want to keep it forever. Put it onto something a little bit more solid. The CD-ROMs, the read once, write once, read forever, kind of an option for you. A little bit more secure CD-ROMs will last 10 to 15 years or so. The problem with CD-ROMs is you can't keep them out of the sun, keep them from getting damaged from boxes on top of them, scratching, stuff like that, because they're a little bit more vulnerable to the elements, but definitely they last longer than a hard drive. Of all of the elements on your computer, the hard drive is going to go first, if anything's going to go. We don't have magnetic tapes anymore, so we can kind kind of scratch this one off the list. Pretty soon we're not going to have this type of drive anymore either. So if you've ever wondered what this solid state drive is, it's kind of like your flash drives. It's like your USB thumb drives, if you want to call it that. There's no mechanical arm. It's a magnetic, but it's not, doesn't run with the same components. There's no hardware that's going to wear out. Instead, it runs a little bit more like the model of the CD-ROM does, actually, where you've got a laser that's going to read it. It's going to write to it. And the technology itself, take an architecture course, take a computer architecture course if you're interested in learning about how the solid state flash kind of works. It's definitely has more prospects for the future, and I would say probably in the next 2 or 3 years. Well, we have computers right now. Sony's have the Macs have the solid states. Sony's do. The new MacBook Air, actually, I'm on a solid state drive actually right now. What's good about that is I can throw it around the room, not that I'd want to, and it's not going to break. Take your regular old notebook with an ARM with this configuration, throw it around the room. You're gonna mess up your hard drive. If the ARM doesn't scratch the surface and destroy all your data, the mechanical parts of it aren't going to be working too nicely after you've shaken it up a lot. So it does wear out. Enough on that. Storage structures. So the disk itself. The disk drives are addressed as one large one-dimensional array of logical blocks. This is how the operating system reads it. So where each logical block is the smallest unit of transfer. So we've got a bunch of data, and the data is located on the disk. All the operating system cares about is this array of data, this array of bytes. And it gets it from the smart media, from the storage, from the disk drive, from wherever it happens to get it from in terms of its secondary access. So this one-dimensional array of blocks is mapped onto sectors for the disk, and it's usually sequentially. So sector 0 is the first sector of the first track of the outermost cylinder, starting part of the disk. Maps, so the mapping proceeds in order through that track, and then the rest of the tracks on that cylinder, and then through the rest of the cylinders from the outermost to the innermost on the disk. And then we have the disk attachment to kind of consider. So host attached storage is accessed through the I/O ports, talking to the I/O buses. So the SCSI itself is a bus. So we have up to 16 devices on one cable as an example. We have a SCSI indicator request operation and a SCSI targets that might perform particular tasks. So each target can have up to 8 logical units. So SCSI actually provides a nice disk attachment technique as an example. It's most commonly used right now for SCSI type drives because it holds a lot. You can put on 20, no, I shouldn't say 20, but maybe 8 disks would be nice. So each target drive has 8 logical units associated with it. On a disk controller, SCSI controllers are fairly sound in terms of the architecture and the design these days. So FC is a high-speed serial architecture, and this is just this is just going to be from an operating system perspective. I'm just giving you a summary of the attachment techniques. Again, take a computer architecture course. If you want to learn more about SCSI or FC or IDE or extended IDE. In terms of SE, you can be switched from Fabric with 24-bit address space, the basic storage network or SANs, hosted attachment for many different types of storage units can be attached using this technique. And it can be arbitrated, it can have a loop in there to loop through 126 devices. So it allows you essentially to attach a lot more than in a SCSI interface, but it's not uncommon to see SCSI drives, SCSI disk cabinets with loaded many different drives on different controllers for a huge server type application for a network. We have network attached storage. So this would be NAS by abbreviation, network attached storage. Storage made available over a network rather than on the local, such as a bus, through the network. We have network file system, CIFs, common protocols, implemented via remote procedure called RPCs between hosts and storage. We need middleware to connect the LAN drives, the storage, to the network in order to facilitate that. So new iSCSI protocols for IP networks. So this out here is the network attached storage, and it's kind of created through the LAN software. I called it middleware a few minutes ago, but the LAN operating system, the RMI, the whatever happens to be the protocol out there that's being used to create the LAN or the WAN, is going to attach the storage and make the resources on the storage available through the network without actually seeing their individual locations. It brings it into this abstraction. Clients connect to this abstraction. This is what the internet looks like, actually. We have a bunch of servers out there. They're all connected through applications. So you're running your, let's say you're doing your shopping on eBay, and your eBay does not run on one server. We have arrays of servers, and all of that stuff is made to look like one network, one solid network. So one of the benefits you get of network attached storage is it's easily modified, easily upgradable, and it's done in modules or units. So one server goes down, the whole thing doesn't go down. You can have a backup server you can bring in there. So a little bit more sufficient, I should say. So in terms of storage area networks, that's a SAN, stands for Storage Area Network. Common in large storage environments, becoming more common today. This would be, well, if I were going to update this lecture right now in this book, and I was going to say a storage area network, and I was going to bring that into 2011 to 2012 time frame. I'd call that a cloud, actually. But a cloud is a storage area network. So maybe in the next edition of this textbook, the term will go away and it will be replaced by the cloud. But what is a cloud? It's essentially a network out there of storage. You have Comcast, I believe that's one of the providers that are doing cloud service now for DVRs. You record something, it's out here. It's out there in this storage array. In your account, one of these servers that are coming into the SAN, Storage Area Network. And it's being accessible through the service and then the clients. So this would be the server running the Comcast network. Out here would be the storage of the DVD you recorded. Your access would run through the server, and you would get on a client end all of your recorded videos, your pictures, your files. So it's kind of a different way of thinking about how you're storing information, because you're not storing it here anymore. Client's no longer storing anything. LAN's no longer storing it. Servers aren't really storing it either. So this is actually kind of the cloud that comes through. But in modern day clouds, it can also actually, the cloud can contain the servers. The servers themselves can be part of the SAN as well. But technically, storage is storage, and a storage area network is kind of an independent, you kind of draw the line a little bit, it's kind of an independent concept. So perhaps in the future, after the cloud terminology gets a little stale, then they'll start using a little bit more specific terms and, to describe, is it going to be storage area or is it service area? So we have software as a service perhaps out here, and we have the storage over here, and we can have all the components uniquely and properly identified. Multiple hosts attached to multiple different storage arrays for flexibility. So these are different storage arrays, tapes, CD-ROMs, hard drives, all types of different storage that connect to create this SAN. And then we have data processing that might use it, web content providers that might use it through the LAN system or the WAN system. And then we have clients over here that would access the WAN to get to the storage through the servers. So, which is kind of interesting. Because when you store it out here, you don't have as much control over it either, actually. Which is kind of the problem with cloud computing right now. A lot of companies are hesitant to take it off of here and put it out here. If they have it here, they got a little bit more control over it through their servers. They pull it off their server or out of their environment and they stick it out here. Then what happens with confidentiality? What happens to restricted access? Who's controlling the access to it? And what if you don't want the public to know about all this stuff? So if you haven't realized it already, Google sort of runs like this. Your email, your photos, everything is your Google Docs, everything is on a SAN running through storage array, and they are one of the biggest data warehousing, data mining actually is what I meant to say, data mining companies out there. What's data mining? Well, now that we have SANs and we have clouds, you know, we'll call it whatever you want to call it. Kind of looks like a cloud, actually. We have data from all sorts of different sources. It's all being stored together. So, and it's accessible because there's not as much security on it versus out here. But take security out of the picture a little bit. Let's say we can solve that problem, and security is going to solve all these clients from getting at only what they're supposed to be getting at. But what about these server applications that have access to everybody's information? Well, they can data mine it. Data mining is just another way of kind of like doing an SQL query on a database. So this is the database, and we can not only, you know, and data mining is actually sort of the opposite. Instead of running a query on a database, data mining says, okay, data, tell us what you've got. And it'll come back, oh, I've got 2,000 pictures of the Eiffel Tower. Okay. I've got 500 pictures of this. And then it can compare all the pictures and take pieces out of the picture. And say, find all the pictures with this person in it, as an example. And this person might be in other different photo albums of other people. And then draw connections between all the people and all the pictures, and you know, and kind of find out information essentially. So paranoid people who don't like to share information, don't want their information to be known to the public, don't use clouds. Companies who have private information, financial information, are not going to stick it out on the cloud. Otherwise, you know, someone can go by and say, well, what you got? What kind of information you got for me? Oh, what's your best product? Where are you buying all your parts and pieces from? You know, you're giving away your trade secrets, essentially. One of the biggest reasons why a lot of companies haven't gone the private cloud, and one last comment here, Amazon is probably one of the biggest server companies right now, selling Amazon space. If you've ever heard of that service provided for a company, that's what this is talking about. This is a picture of it right here. Amazon is one of these storage arrays. It's coming into it. Because they're cheap. They're one of the first into the market, and the name's gotten out, and everyone's outsourcing. So let's talk about disk scheduling. Let's go back to the local area network. I'll get off the cloud for a second. The operating system is responsible for using the hardware efficiently for the disk drives themselves. This means having fast access time and bandwidth. So having great disk bandwidth and access time. Access time has two major components associated with it. We have seek time and rotational latency. So the seek time is the time for the disks. Time for the disks are to move the head to the cylinder containing the desired sector. Seek time is part of the spec that you're going to see. How long does it take for the arm to move around? Well, that's a function of the disk hardware and the manufacturer who made the disk. Some disks move faster than other disks. Some disks move fast and aren't very careful. Some of them are more careful. Some of them are more prone to errors than others. Rotational latency is another vocabulary word. It's the additional time waiting for the disk to rotate to the desired sector, to the disk head. So the rotational speed is also wasted time. It's a time factor. So we want to minimize the seek time, and the seek time is the seek distance. So if we know it's going to take time to find something on the disk because the arm has to move, we can write an operating system that rates the disk that minimizes the number of times the arm has to move. Sounds pretty good. So then we have algorithms to do this, which is what the operating system component is all about. We also want to minimize the disk bandwidth, only bring the sectors we need and bring the right sectors. So the disk bandwidth is the total number of bytes that are transferred divided by the total time between the first request for service and the completion of the last transfer. So that's a calculation that we're going to do in terms of the total bandwidth requirement. So now what I'm going to do is kind of compare and contrast a couple of different algorithms. And this is what the operating system, so if you're building an operating system, you have to consider, because a really bad design is going to wear out the hardware because it's going to make the arm move unnecessarily. So several different algorithms exist to schedule the servicing of the disk I/O requests. So we're going to illustrate them with the request queue What are these request queues? They're numbers. So these are areas on the disk. Let's say this is a file, and the file is not stored contiguously. If the file was stored contiguously on the disk, which is why a defrag kind of helps you a little bit, then it doesn't take as long to get it, because we find the starting position of the file. Let's say the file was number 98, started here, which this is the starting position of this particular file we're trying to get from the disk. This would be 99, 100, you know, and we wouldn't have to calculate. We just have to know the length, and we can just go. So we move the arm to one position or read it. That's very efficient. But who in the world can store stuff contiguously? It's kind of like memory. It's kind of what we talked about in terms of virtual memory. Hard to use it contiguously. We're not making efficient use. The pro to that is that it's fast. The con is that we're not really utilizing everything we can on the disk. What happens if the file grows? It can't. You know, what happens, you know, same problems we have with virtual memory, we have with secondary storage in terms of contiguous memory allocation. So nobody uses contiguous allocation anymore. It's all spread out all over the disk. And we have a starting position on the disk because we don't always have to, you know, a brand new, when we turn the computer on, in fact, when we turn the computer on, we don't even know where the arm of the disk is because we're not going to move it unless we have to move it. And so like this particular example, the head pointer is at space 53, and all these may be just byte locations on the disk. So if we're starting at space 53, we're going to have to move to 98, move to 183, if we're doing it in this order. If we're doing it sequentially, which is one of the things to think about. So first come, first serve. So given that string we just looked at a few minutes ago, the goal here is to find all these bytes that equate to the one file that we're trying to get, with minimizing the number of head movements, because the head movements are going to give us our seek time and our access time. So the bandwidth we can't really, you know, we can only support so much bandwidth down the bus channel. However, that's given to us already by the problem. So this is the data that we have to go get. So here's our queue, and that's that string I just showed you a few minutes ago. The head starting at position number 53. So here we are at 53. So on a first come, first serve, it would go to 98, and it would go to 183, and it goes back to 37. Ooh, but it was right here. If it knew it needed 37, it could have gone here first. So we're going, this is the arm, if you can imagine it, just the arm going back and forth over the disk. This is exercising it a lot, first come, first serve, because of the positioning. So obviously we could reorder the list. We could say, you know, take this and, you know, okay, 37, which one's close to 53? You know, and go backwards and then go forwards. So that's what the different algorithms are doing. It's comparing, and what I'm going to go through is a couple more techniques, but show you how to compare them first. So in terms of what we're looking at here, we would add up all the arm movements. We would kind of figure out in terms of the consistency of where we're going back and forth, you know, how much time is it going to take. So it shows how the movement on 640 cylinders is going to look. We have the shortest seek time first approach that we can take, and that approach is going to select the request with the minimum seek time from the current head position, as I mentioned before. That was the alternative approach here. So if we're at 53, the minimum seek time is going to be 37. And then the next one after that, next one after that. So we end up with a little bit more efficiency. The shortest seek time first scheduling is a form of shortest job first scheduling. May cause starvation of some of the requests. It's the same problem we have with virtual memory, actually, because the bigger numbers, you may never get to them. So might just be picking up all the stuff that's close to the head. And so someone's going to have to wait for that entire file, because imagine we have multiple requests that are hitting it simultaneously from multiple users, multiple processes. Anything that's accessing that secondary storage is sending in a string and says, hey, I need to go get all this stuff from the disk, give it to me. And the servicing algorithm goes out and gets those bytes. So illustration shows a head movement on a 233 sector disk. If we go here, we started here, we go to 37, and then we go to the next one, which was going to be 14, and then, you know, we can go through the numbers and kind of, you know, you're minimizing the amount of head movement at this point, but calculating out which is the next shortest job might take more time. So imagine this is an algorithm that has to perform in real time. We're trying to make it run as fast as possible. Or we can have the scan, aka the elevator. So what is an elevator? Well, it goes up and down. You can think about the problem scenario. It's kind of like the elevator, sort of like the arm on the disc. Is that some elevators do go up, down, up, down, up, down, up, down, or they go all the way up to the top, then they go all the way down. Old style elevators actually used to, if you wanted to go down, you had to go up first. You went all the way up to the top, and then you went all the way down, and it didn't stop on each one of the floors because it wore out the mechanism. So the disk arm can start at one end of the disk and moves towards the other end, servicing the request until it gets all the way to the other end of the disk where the head movement is reversed, and then servicing continues in the opposite direction. Sometimes called the elevator algorithm because it works like an elevator. So here's the illustration shown on a head movement of 208 cylinders. So the cylinders have been adjusted given the size of these disks, and this is just for illustrative purposes. So if we started with 0 and we moved this way, we would pick up stuff until we got up to 199 and say, oh, that's the last one. Or we got to the end of the disk, actually, and we turned around and come back the other way. So that's called the scan. The circular scan provides a more uniform wait time than the scan. It's a variation. So the head moves from one end of the disk to the other, servicing requests as it goes. When it reaches the other end, however, it immediately returns to the beginning of the disk without servicing any requests on the return trip. So it immediately goes back to the beginning instead of picking up on the other. So it only services in one direction instead of both. So it provides a little bit faster access in some cases. Treats the cylinders as a circular list that wraps around the last cylinder to the first one. Here's our C-scan. So what we did is we went one direction and we went all the way back, and then we went this way. And actually, in this particular case, this was helpful because we had this over here. I didn't need to pick up anything. So it was faster to go back to the beginning and then pick up these two at the beginning. So that would be a C-scan or circular scan. So it makes it as a C-circular. Or we have the C-look, a circular look. So it's a version of the C-scan where the arm only goes as far as the last request in each direction. So instead of going from the beginning of the disk to the end of the disk, it looks at the bytes that it needs to get, starts at the beginning position, which I believe is 37 from memory, and it goes to the end. I can't remember what the end is, but we'll probably see in the next slide. Instead of going all the way to the end. So without first going all the way to the end of the disk, here it is. It stopped at 183 instead of 199. So it stopped at 183. This is handy because why go past it if we don't need it? However, how are you going to find that out? So the algorithm has to look at the list. Actually, almost has to sort the list. So time taken to sort the list is going to add to the inefficiency. Do you want to sort? Is it going to be more efficient to sort the list to figure out what you have, or to have it be just dumb and go from one end to the other end? So it depends on how many items are in the list, how easy it is to sort the list. If you've got a ton and one of them is 198, let's say, for example, forget it. It's probably faster just to go back and forth than it is to actually figure out, well, what's the last item? If the last item is only 37, or 37's over here. If the last item is like 65 or something, where I have my cursor pointed, that is a significant time savings, not having to go to the end, and that might make it worthwhile. So selecting a scheduling algorithm for your operating system. So the shortest seek time first is common and has natural appeal to it, but you have to sort the list. The scan and the C-scan perform better for systems that have placed a heavy load on the disk. If you're reading a lot from the disk, the scan or the C-scan makes a lot of sense. Because if the arm is going to need to move a lot anyway, you might as well control the flow. Might as well just have it go from one end of the disk to the other end. A nice, smooth, easy movement that it can do 1,000 times, a day, or whatever. And then you're going to minimize the breakage on the arm. Performance depends on the number and the type of requests, so it might be application specific. Requests for the disk service can be influenced by the file allocation method as well. As I mentioned before, contiguous file allocation. Not so efficient, however, minimizes the algorithm, the expense of the scheduling algorithm for the disk. So if we know where the blocks are, we don't have to go all over the disk for them. They're right here. So the disk scheduling algorithm should be written as a separate module of the operating system, allowing it to be replaced with different algorithms as necessary. So either the shortest seek time first or the look is a reasonable choice for a default algorithm for implementation. So, in terms of the disk management, and now let me go back here for another second. So after we've looked at, before I get into disk management, after we've looked at a couple of different algorithms, and the point of the algorithms is the seek time associated with movement of that head to go find the disk. Imagine how nice solid state is. We don't have to worry about moving the mechanical arm anymore, and the seek time's a lot faster. So the read access to it, a lot faster. So with modern day improvements, perhaps we're going to see in the future better algorithms, perhaps. So what are modern day operating systems using? Hard to tell. Probably a combination or a variety. The operating system itself has an algorithm, though, that's designed within the operating system to go get information off that hard drive. So depending upon the type of drive it is, some of the characteristics of the algorithms might see some significant improvements, hopefully, as we're not so concerned about moving the arm all over the place anymore. Disk management. So low-level formatting or physical formatting. This is partitioning. Not making directories like last week, but actually taking the hard disk and dividing it out. So dividing a disk into sectors, and then the disk controller can read and write to different sectors. You're making it smaller. This is why people in the beginning took those, in the beginning it was kind of funny. We had 1 gigabyte drives, 2 gigabyte drives, and they partitioned them. So if you had a 2 gigabyte drive, you partitioned them into 1, or 500 megabytes each. You made 4 drives out of it or something, and you kind of, people took a lot of time thinking about all this stuff. Well, in theory, it's kind of outdated. Old operating systems couldn't read a drive past a certain amount anyway, so you had to partition it. And then the concept was, well, you didn't have to seek as far in that partition, which is kind of true if you think about it. But now that we're not worried about disk head movement, we're not worried about seek time, and operating systems are now built to hold a lot of memory because their files are bigger now. Multimedia files can take up a gigabyte. 1 gigabyte, one file. You're going to put one file on a disk. So now we have a 300, 500 gigabyte drive with gigabyte files on it. We're not so concerned anymore. And so we're going back to more contiguous, to more less efficient storage mechanisms that lend themselves a little bit better for the retrieval. So going back to, because I just remembered it, what I said about defrag. The interesting part about defrag, you make the disk smaller. So if you don't have anything written to the disk and it's empty, the operating system doesn't necessarily have to read it. So if you take all the files and you move it closer and put them all together contiguously, so defrag takes non-contiguous disks and makes the storage contiguous. It tries to do it for files. It'll locate all the blocks together, depending upon how good the defrag is. Makes it easier to find the files. It will improve the access speed because it won't have to look as far. And it doesn't go and use the entire search space of the drive. If you stick a huge hard drive on your computer and you fill it up with a lot of stuff on it, you actually take up 300 gigabytes of space. Anything on the disk will take longer to access in theory. Doesn't matter what operating system you're using. If you have an empty drive, you partition an itsy bitsy little partition on there and you make a little C drive on it with 500 megabytes and you only use that, it will be lickety split. It will be very, very quick to access, even though it's a 300 gigabyte drive, because you're telling the operating system only use this little part of it, skip the rest of it. which is kind of interesting. That's why people get carried away with partitioning, because, you know, well, some people have organizational control issues, but other people use it so it makes the access more efficient. It makes it so that the drive, if you're only using one little drive and it only has 500 megabytes or 1 gig on it, the access time is a little faster, because even if it's using a scan algorithm, it doesn't have to go all the way to 300 gigabytes. It's only going to 1 gigabyte. So it's shorter search space, makes it easier to find stuff. So you can use these tools to partition. Partitioning just tells the operating system all this space, call this little sector, call this little section A, call this little section B, call this one C, or something. So you use a disk to hold files. The operating system still needs to record its own data structure on the disk. The operating system needs to know the format. So you format the disk for the operating system for the file format that you're going to use on the disk. You partition the disk into one or more groups of cylinders. So it's logical partitioning, or making a file system is what you're doing. The boot block is usually at the beginning and you have absolutely no control over it. It is usually the first 32, 64 bits or so of the bytes of the drive that's reserved for the operating system. That's where your boot ROM is stored. In fact, when your computer boots up, the last thing the hardware does is look at the boot sector of the first hard drive in the sequence and say, well, what do I do now? And the boot sector says, oh, go run command.com and go load up Windows. Or, you know, run init and start a Linux kernel. Or, you know, basically the boot sector is the part that starts your operating system. It's actually kind of mechanical if you think about it. So the boot block initializes the system. The bootstrap is stored in the ROM. It's actually stored on your hard drive. We have a bootstrap loader program. That's a little menu that comes up. It says, hey, you know, would you like Windows or would you like Linux? Like a grub menu or something. And then the methods such as sector sparing are used to handle bad blocks. But basically, mark the block bad so it's not used for any storage and it's not accessible. And the operating system essentially just ignores the block because it's bad. I'm not going to read it. So here's booting from a disk in Windows 2000. Well, that's kind of old. We have the MBR master boot record. Partition 1, partition 2. Master boot record actually just keeps track of the different boot partitions. This is still the same kind of concept that's being used in Windows 7 and in the OS X actually too. There's a master boot record that keeps track of the partitions. Partitions keep track of in sectors, keeps track of parts on the disk itself. Just basically puts a label on it and says this is C, D, E, and F or whatever. This is why virus protection programs love to protect the master boot record. In fact, if you have a virus program, hopefully you do, everyone should. The old primitive viruses used to erase this, or used to put a picture in here. So when you turn your computer on, you get this little lovely picture that shows up instead of your operating system running. Or just to take and corrupt it somehow, you know, or load a different one on there, and then all of a sudden your entire disk is unusable. Because the master boot record is keeping track of all the partitions. You mess up one of the partitions, you're gone. And the information on that partition is not going to be readable. So the boot code, the partition table, all you have to do is mess up either one of the two. Easy for a virus creator to do. That's why most people won't allow you to write to it. So once the boot sequence is complete, what ends up happening is the antivirus program puts a lock on it, checks it, makes sure that nobody can write to it while the operating system is running. So if you download a file, it can't go and write to it. Without virus protection, you can write to it, actually. You can write a little C program that writes to it. No problem. You just tell it to go to this particular part of the disk. It's regular file I/O. You open it up, you write to it. So little system calls will do it for you. So we have this thing called swap space. So if you've ever installed a Linux kernel, you had this option to do what's called a swap drive. We talked about swaps. We talked about swaps with virtual memory. It's a part of the hard drive that is used to kind of mimic virtual memory instead of being used for storage. So it's formatted differently. So it's used as hard drive space, secondary storage, but the operating system doesn't see it as secondary storage. Instead, it's identified as a swap, and the virtual memory manager uses it to swap out of virtual memory temporarily. So it gets formatted differently. It's unusable, cannot be used by the long-term storage management. So swap space, the virtual memory uses the disk space as an extension of the main memory. It can be carved out of normal file system, or more commonly it can be a separate disk partition. Very common these days to have it as a separate disk partition, actually, or a separate drive, hard drive itself in some Linux systems. So in terms of swap space management in 4.3 BSD, which is actually an older version of the BSD that the Mac systems actually use, allocates the swap space when a process starts, holds the text segment or the program and the data segment, and actually kind of uses it natively while the program processes are actually running. Kernel uses the swap maps to track swap space use. So layers 2 allocate swap space only when a page is forced out of the physical memory, kind of like what we talked about with the virtual memory management. Not when virtual page is first created, but only after we run out of memory. So Windows has the option actually to use a swap space as well. You can configure it in the control panel system icon. There's a virtual swap space option. You can actually create a swap area and use a swap. And it's done the same way as you would do it in a Linux system. Here's the data structure for swapping on a Linux system. We have the swap area. We have a page slots. So these swap areas would hold pages. This is basically the equivalent size of a virtual memory page. So your memory is partitioned into pages, and that pages are holding frames, and that frame information is a certain format in terms of its size and length. So the swap space is just formatted identically to the virtual memory. And how it's done is done through the operating system configuration. So the swap partition or swap file is kept, and it kind of mimics, so there's a one-in-one kind of connection that goes on between the virtual memory, the swap map, and the swap area. So we can easily swap things in and out. So RAID, a multiple disk providing reliability via redundancy. So it's tons of disks strung together to essentially hold the disk image, and the disk image is being facilitated on the physical medium of the disk. Kind of like how virtual memory works, where we have a ton of pages that are created out of the abstraction of the physical memory, and we can use the physical component of the memory to process the information. Well, this is kind of the same concept, except, for example, if a disk goes bad, well, actually, if a memory goes bad on your computer, you just swap it out, put a new one in. Or, let's say, for example, you want to upgrade, you just add more memory. You don't have to actually copy anything, change anything. So it's basically using your hard drives like this. So hard drives go bad, you just take a hard drive out, put a new one in. Or let's say, for example, you want to make it bigger. You just add another hard drive, and now you have more space. So the image itself gets loaded when the operating system is actually running. The image gets loaded on, and the physical medium of the disk is used to support the image in terms of its storage. And it's stored in files outside of that, and when the system is actually created, when it's initialized, this array is used as one disk altogether. So the RAID is arranged into 6 different levels. So several different improvements, and this is kind of an old concept that's still being used today for servers. I mean, who makes a quadrillion, billion size disk? Nobody does. So you take the biggest disk possible and you add them together in a RAID, you make a huge storage area. So we have in the disk use techniques that involve the use of multiple disks working cooperatively together. The disk striping uses a group of disks as one storage unit. So RAID schemes improve performance, improve reliability, storage system by storing redundant data. You can also have what's called a mirrored disk. A mirrored disk is nothing more than an image that's copied on multiple hardware. So it's mirrored And each time you update it, it has to get updated everywhere, so the mirror gets updated as well. But the disk itself, the RAID, is more along the lines of taking a bunch of disks and stringing them all together and loading a big old image on them all, having them all work together. So mirroring or shadowing keeps duplicates of each one of the disks. Block interleaving parity uses for less redundancy. So it depends on what you're trying to achieve as to what type of RAID technique or what type of level you're going to implement. At level 0, we have no redundant striping going on. We just have a bunch of disks loaded here. At level 1, we can have each one of them mirrored, which means for each one of the hard drives, we have another hard drive that is taking a copy of it and storing it. Why? Because if we lose the original, we've got the copy. We can load it back onto the original. So this is, you wouldn't do this for your own computer, but you do it if you were Wells Fargo or something, and you wanted to make sure that you never, ever lost any data. So this makes it completely redundant and makes it more reliable. More redundancy, generally the more reliability as long as it's held consistent. Here's a RAID 2 style where I have memory style with error correcting code that's added in. Bit interleave parity going on here, and as you go through the RAID levels, you add different features in terms of what's going on. And for the purposes of the final, as I mentioned earlier, I'll tell you what you need to know in terms of secondary storage, and I don't believe I have any RAID questions on the exam, but it's nice to know the concept. However, I'm not going to ask you nitty-gritty details about each one of the RAID levels, and this material, by the way, is a bit outdated in terms of the levels and the configurations, so I should just skip through it because it is outdated, but the concepts aren't. So striping, to stripe it, to mirror it, still is a viable way of creating redundancy and creating fault tolerance. So stable storage implementation, your write-ahead log schemes require for stable storage. To implement stable storage, you replicate information on more than one non-volatile storage media with independent failure nodes. It's kind of like keeping an off-site backup. That would be considered a stable storage implementation. So you're making it stable, you're making it so it can't go down, it's mirrored somewhere, it's off-site, it's not on a different disk controller. You update the information in the controlled manner to ensure that you can recover the stable data after any failure during any data transfer or recovery that might exist. We have tertiary storage devices. Hardly anyone has heard that word before. However, you all use it. CD-ROM, DVD, CD-ROM. I can't even say it. Tertiary, which is the formal word for it. Kind of hard word to say. Nobody uses it. Just call it a CD-ROM. Low cost in defining characteristics. So generally, it's built by using what's called a removable media, floppy drives, CD-ROMs, common examples, floppy drives, CD-ROMs, other types, DVDs, all falls into the same category, Tertiary, whatever, storage media, removable disks. So these could be hard drives as well. You can actually update this, take the word floppy drive out, replace it with thumb drive or USB drive. So thin, well, we don't have floppy drives anymore, but in the old days we had these little thin coated plastic-covered magnetic discs that were in a protective case, and we slipped them in the drive and pulled them out of the drive. Now we use USB ports. We don't have any more floppy drive readers. In fact, I don't think they sell computers anymore with floppy drive readers. And of operating system lectures, this is the most outdated one possible because this is where most of the improvements have occurred in the last decade. So now USB drives, replace the concept. Get rid of this stuff. Actually, USB drives, what are we up to, like 4, 8, 16 gigs for reasonably priced. Actually, you could probably get one for free. 2 gigs, 4 gigs are probably free right now. You can buy one, get one free, or just go in a store and they give it to you as a promo. But in the old days, 4 gigs was, you could probably, 1 gig, you could probably pay a couple $100 for a 1 gig USB drive about 5 years ago, or 10 years ago maybe, who knows. Removable magnetic discs, don't have those anymore either, so. Magneto-optic discs records data on a rigger platter coated with magnetic material. So laser heat is used to amplify large, weak magnetic fields recorded by laser light. So laser discs. Laser light's also used to read data. So magnetic, optical, these are some of the experimentations. We don't even have laser discs anymore either. Remember the laser disc? It was like a cross between, it was about the size of a vinyl disc. We don't have vinyl anymore either. Music, you buy an album, it came on a vinyl plastic, thing. you put on a record player. Then they said they made something like this. It was the size of a vinyl record, but it was made out of a thicker material than what you normally see on a CD-ROM. So it looked like a CD-ROM drive, but it's called a laser disc, and you had to get a special laser disc player for this. It was a laser or magnetic technology. Well, the deal with that is it just stored a lot. So it was able to store a lot more data, and it was able to, had two sides to it. You can store on both sides, and you actually took the disk out and you turned it upside down and you put it back in the drive and you used it, and you just pressed play and it continued, kind of like flipping the tape on a VCR. It gave you CD quality. So then they came out with the DVD. Now we have dual-sided DVDs, and now we have HD TV, HD, high definition. So we've definitely made a lot of advancements recently within the last decade. Optical discs do not use magnetism. They employ special materials that are altered by laser light, laser discs. So, read once, write once, read multiple times. Warm, kind of sounds like a virus. Read once, I want to say read first. Write once, read many times. It's kind of like those not the read writes, but the writes. Not the read writables, but the write disk. So the CD-ROM-Ws, write. So the data on a read write can be modified over and over again. On a warm, the disk can be written only once, like the DVDs, and then you can have read write DVDs now, but the concept is the material doesn't have to be as strong. If you're only going to make it so it writes once, if I say this in the right order, then it's set in stone. Then you can use a lower grade kind of plastic coating on the magnetic or whatever it is, whatever substance you're going to put, and don't quote me on the substance, take an architecture course for that. It makes it so it's cheaper, and it's like CD-ROMs. I mean, not CD-ROMs. Music CDs are warms. You can't write to it after. You can only read to it after you've written to it once, and it's durable, a lot more durable. Some of those discs that you use, the read-writable discs that you make backups with, terrible way to do a backup actually, because only after a certain number of writes the thing gets corrupted. It just won't write anymore because the structure, it gets broken down and it gets worn out actually. So thin aluminum film sandwiched between two glass or plastic platters. Well, that thin aluminum film will get to a point where you've read it. When you write it, and it gets damaged through use. So you want to make sure if you're going to really keep a backup of something, use one of those write once, read forever discs. Put it on there and put it in a nice little plastic case and store it in a dark place away from the heat so it doesn't get damaged. And keep it out of water. You don't want to rust the thing either. So to write a bit, the drive uses a laser light to burn a small hole through the aluminum. The information can be destroyed, but not altered, which is interesting. So very durable, very reliable. So read-only discs such as CD-ROMs, well, now we have ones that aren't, both of them are rewritable now. They come from a factory with data pre-recorded on them. Those are the most protective type of discs because you can seal it in there and it'll last a lot longer than the read-writable ones. So, tapes, nobody uses tapes anymore, but tapes were popular. magnetic tape. So that compared to the disk, the tape is less expensive and holds more data. That was the old days. Now the disk holds more. So more random access is much slower. Do you remember 8-track tapes? And then we had CDs. No, we had, cassette tapes from the 8-tracks. And then we had mini cassettes. 2 spindles, kind of like an old-fashioned typewriter with a ribbon. With this ribbon that was around it, and the ribbon moved from one spindle to the other. And again, we're talking about the quality of the spindles, the plastic that's being used. How many times has that tape actually been used, been written to? And they were, you needed a special reader to slip it in to actually make the thing work. So obviously, too mechanical, breaks down. So the modern trend in all of this, long story short, is to get rid of the mechanics. Make it so that you have a light that's not touching the surface, that can't touch the surface. So light readable sources that is not moving, that is solid, that it doesn't have any movable parts, and it will last longer, essentially. So large tapes, well, we don't have to worry about tapes. We don't have tape library. We don't have any of this stuff anymore, so I'm going to avoid it. So disk-resistant files, Operating system issues, let's talk about that. Many operating system jobs are to maintain physical devices and to present a virtual machine abstraction to applications, meaning that the storage is held separate from the applications, held separate from the operating system. For hard drives, the operating system provides 2 abstractions: the raw device, an array of the data blocks that can be read as a device, and then the file system. The operating system queues, the schedules, the interleaving, the requests for several different applications that are working. And the file systems themselves are more than just what you'd think, actually. Operating systems have to support music files, have to support VOB files from DVDs and stuff, and all sorts of different types of translations. And so it's not just the operating system, it's also the applications that are working with the operating system. They're sharing in some of the work. So when you slip the DVD into the drive, the operating system's got to notice the device, it's got to read the device, it's got to give an abstraction of the file of what it read, and then an application has to take over and has to actually run the movie or run the music, whatever happens to be on that device. So we have the application interface. Most operating systems handle the removable disks almost exactly like fixed disks. In fact, even Windows, if you take a removable disk, a thumb drive, USB drive, you stick it in your computer, you get a new drive letter. C, now you got D, E, and F. It just loads just like a regular old hard drive, actually. The Mac system does it in a very similar fashion as well, except for you get a little icon. Actually, you get a little icon, I think, in Windows, too, on the desktop. So a new cartridge is formatted. Empty file system is generated on the disk itself. Tapes are presented in raw media storage. So I'm not going to talk about tapes. Since the operating system does not provide file system services, the application must decide how to use the blocks, must decide how to use this. So the applications take in and pick up where the operating system left off and provide the ability to recognize that file and to use it somehow. I'm going to skip tape drives because we don't have them anymore on the market. File naming are mostly application specific and also operating system specific. Issues of naming files on removable drives, especially difficult when you want to write data on a removable cartridge on one computer and then take it to another computer and use it. Was a problem in the old days. Nowadays, almost every operating system recognizes almost every file type and file name, which is kind of interesting. So in the old days, when we had Windows with a 7x3, so the name of the file was 7 with a 3 extension. Now we have extended file name support. So we have, as the files can be as long as you want, they can have spaces in them, and not as many restrictions, and you can just take that file over to another computer, Mac system, and it reads it just fine. So that's really an outdated concept as well. So generally, leaving name space problems unresolved, and we don't have those issues. So removable CDs, standard. Actually, everybody calls the names the same, so everything's pretty standardized these ways. Hierarchical storage management, still going on. We have a hierarchical storage management in our computers. We hold all of our programs and applications on different drives. In fact, sometimes some of your Windows installs have a separate partition that holds a backup of the operating system. And you hit the recovery option when you boot your computer up, and it goes to the backup partition, and it just reinstalls everything automatically for you. Which would be hierarchy because it's not being used. It's being used to operate support the operating system. We also have we also have swap drives and things that are being used for the operating system. We have a hierarchy of hard drives that might be being used. Thumb drives are going to be loaded in at a certain different area of the system. So hierarchical storage itself extends the storage hierarchy beyond the primary memory and the secondary memory to incorporate there's that word again, removable, Tertiary, the removable storage, let's call it that, usually implemented as a jukebox or tapes or removable disks. So we can add stuff to it by taking and we're seeing more of a hierarchical system these days, especially a networked hierarchical system. Because when you log on to the internet and you access your cloud, you're essentially using a hierarchy. You've got your computer, and then you've got your network space, your drive out there, your iDisk or whatever it is, depending upon the platform that you're on. It's not on your computer, but you're accessing it. And maybe you're running programs and things on the internet that aren't on your computer, but it's in the hierarchy of your storage, and you're saving information in that hierarchy that may not necessarily be local. So usually incorporated through extending the file system. So small, frequently used files remain on the disk. Applications may end up being on the network eventually, but large, old, inactive files are archived in the jukebox. So the hierarchical storage management is usually found in supercomputing centers and large installations of enormous volumes of data. You're going to put it in a hierarchy. It makes it easier. As an abstraction, it makes it easier to understand. So, two aspects of speed in the Tertiary removable storage are bandwidth and latency. So bandwidth is measured by the bytes per second. So we have sustained bandwidth, the average data rate during a large transfer, number of bytes divided by the transfer time. The data rate when the data stream is actually flowing. So effective bandwidth is the average over the entire I/O time, including the seek or the locate time. So in terms of the drive's overall data rate. So we're interested in speed because we have different channels. As an example, if you load a USB drive, you don't want to run an operating system from a USB drive, by the way, although a lot of people install Linux on USB drives. They plug it in their computer and they boot to the USB drive. Slow. USB support is the slowest of all. So IDE, SCSI, all those buses are faster. They support faster seek times, faster transfer times, so your operating system is going to run really slow if you run it from a USB drive. But if you're just playing around with it and you kind of want to see it run, and not a good solution in the long run, but okay to play around with. But a lot of people, because those USB drives have become so large, people are installing operating systems on them and they're booting to them. And that's it's kind of a serious slow operating system if you think about it, just because of that USB bus channel. So latency time is the amount of time needed to locate the data. And I'm just talking about the channel time, the bus time. I'm not even talking about any of these other stats when it comes to USB. Access time for the disk, access time for the tape. You don't really need to know any of this stuff, but consider you can calculate out time to move the data, find the data, write the data, read the data, random access within the tape itself. The low cost of the storage itself is a result of having many cheap cartridges share inexpensive drives. Loading on new drives. Usually a removable drive is cheaper than a main drive, but it's going to run slower, bottom line. And the last quote is kind of relevant. Removable library is best devoted to storage of infrequently used data because the library can only satisfy a relatively small number of I/O requests per hour. So most people who want to move things away and put them on disks and stuff, if you're not going to use it very often, take all your stuff, all your photos, copy them on the DVD ROMs and store it that way. and it'll last longer. It'll be more reliable in the long run. But when you want to find a picture, you have to find the disk that it's on, load the disk up, and it's slower to read it from the disk than it is from the hard drive, which is what the slide was saying. But it's safer. So just because it's faster to read it from your hard drive doesn't mean it's going to be there forever. So reliability. This disk drive is likely to be more reliable than a removable disk or tape drive. That's true. Optical character drive is likely to be more reliable than magnetic disk or tape drive. That is correct as well. Head crashes as a fixed hard drive generally destroys the data. Yep, which is why when you throw your computer falls down. If the head arm hits the disk's surface, it's called a crash. It's going to damage it. Failure of the tape drive, optical drives, often leads to data cartridge unharmed, usually. So hard drives themselves are kind of vulnerable. So the cost main memory is much more expensive than disk storage. The main memory is talking about that virtual memory. Disk storage is farther away from the CPU. It is the cheapest memory. So closer to CPU, more expensive. Farther away, cheapest you can get. Really cheap USB drives now. So the cost per megabyte for hard drive storage is competitive with magnetic tapes. If only one tape is used per drive, well, you can probably scratch all the cost estimates on magnetic tapes since how they don't really exist anymore. In fact, you can probably scratch most of the stuff related to hard drive cost on this slide as well, and don't even bother reading it because costs have we seen through Moore's law. You know, every year, processing power and doubles and hard drive space doubles, and the cost goes down by a half. So one of those, I don't know if it's Moore's law, is one of those laws out there basically predicting the growth, exponential growth of technology and the way that the costs diminish. I suspect probably in the future, well, you can probably see it now with just the price of those thumb drives that have gone down in size and how big things have gotten. So it's kind of held true. Things kind of double every year. So price per megabyte of DRAM, well, yeah, went down completely. So things get bigger and bigger and cheaper as technology grows in terms of computers. Price per megabyte of magnetic hard drive, 10 megabyte hard drive, wow, $100, yeah, is it? Number of megabytes, dollar per megabyte, wow. Actually, I remember there used to be $200 for a 20 meg, 10, I don't remember the 10s, but the 20 megabyte hard drives back that I can remember were like $250 or something like that to add one on. Now you can spend $100 and probably get like a 200 gigabyte one or something. And then perhaps another 5 years from now, it'll be like 50 cents or something. No, it'll probably be like $20 or $30 for a 300 gigabyte hard drive, perhaps. It just seems how things are going. So the megabyte, tape drives you don't have to worry about. So that is everything I ever wanted to know about mass storage systems.